All right, let's dive in. We're going to pull back the curtain on a piece of tech that is, right this second, shaping what you see and hear, and you probably don't even know it's there. We're talking about the secret math that cleans up your music, sharpens your photos, and really makes our entire digital world possible. So yeah, let's see how it all works. So, let's start with a little question. Picture this. You've got your favorite playlist on, you flick on the noise cancellation, and poof, the world just fades away. Later, you snap a photo, and with one little tap of the sharpen tool, it goes from kind of blurry to totally brilliant. Now, these two things seem completely unrelated, right? But what if I told you there's an invisible thread, the exact same core idea, connecting them both? Well, the answer is one of the true unsung heroes of our digital lives, the digital filter. It's this powerhouse working behind the scenes in practically everything we use, from our phones and our cars, all the way to critical medical equipment. So what is it exactly? Well, you can think of it less like a coffee filter and more like a recipe. It's basically a set of mathematical instructions. It takes a stream of numbers, say the data from a microphone or a camera sensor, and it follows a very specific procedure to turn it into a new and hopefully much more useful sequence of numbers. And its job description is, well, it's huge. In a hospital, it's the thing that cleans up all the electrical noise from an EKG so a doctor can actually see a clear heartbeat. On your phone, it's what keeps your call from spilling over and messing with someone else's conversation. From boosting the bass in your music to making your photos pop, these filters are just constantly at work. But here's the thing. Digital filters weren't always the way we did things. To really get how powerful they are, we kind of need to look at what they replaced. This is the story of a massive leap, from clunky physical circuits to elegant, flexible software. See, in the old days, filtering was a physical job. I'm talking about analog filters, built from actual resistors and capacitors, stuff that could wear out or just drift if the temperature changed. And get this, if you wanted to change how the filter worked, you had to literally break out the soldering iron. But digital filters? They're just software. They are rock solid, perfectly predictable, and if you want to change one, you don't rebuild it. You just rewrite a few lines of code. That flexibility right there, that's what changed everything. So, how does this software magic actually happen? You might be picturing pages and pages of complex math, but here's the beautiful secret. It all boils down to an incredibly simple recipe. This diagram here shows the entire journey. First, you've got a messy, real-world analog signal, like sound waves hitting a microphone. That has to be translated into numbers a computer can actually understand. That's the job of the analog to digital converter, or ADC. Then, our digital filter, the processor, works its magic on that stream of numbers. And finally, to hear it, those clean numbers get turned back into a smooth sound wave by a digital to analog converter, or DAC. From messy to clean, all in just a few steps. Okay, let's zoom in on that processor block because that's where the real secret sauce is. And you're not going to believe this, but every single digital filter in the world, no matter how complex it seems, is built using just 3 ridiculously simple operations. Our first building block is the multiplier. Its only job is to scale a value up or down. That's it. It's basically a volume knob on a stereo. Simple.
Next up, we have the adder. And as the name suggests, it just combines 2 or more signals by adding their values together.
Super simple. And finally, we get to the most important ingredient of them all, the delay. Now, you might see this written with some funny-looking math symbols, but all it means is memory. Its entire job is to hold on to a number for just one brief moment, one sample cycle, before passing it along. This simple act of remembering the past, well, that's the key to everything. So let's put our 3 little building blocks to work. We can make a simple but very useful filter called a 2-term average filter. First, we take the current number that just came in. Then we use a delay to grab the number that came in right before that one. We use an adder to combine them, just add them up. And finally, a multiplier scales the result by 0.5. In other words, it cuts it in half. That's it. By averaging 2 numbers in a row, this little filter smooths out any sharp spikes, which is a fantastic way to reduce high-frequency noise. Okay, so we've got our 3 building blocks. Now, depending on how you arrange them, you can create 2 main families of digital filters. And the difference between them, it all comes down to one simple idea. And that one key difference is feedback. The question is, does the filter make its decisions based only on the new information coming in, or does it also take a peek at the clean signal it just put out? That one choice creates 2 very different kinds of filters. This table really breaks it down nicely. On one side, you have fill filters. Now, these guys do not use feedback, which makes them incredibly stable. They will never, ever spiral out of control. Their superpower is preserving the timing of a signal perfectly, which is absolutely critical for things like high-fidelity audio. On the other side, you have IIR filters, and they do use feedback. This makes them way more efficient. It's like a computational shortcut, but you have to design them very carefully so they don't become unstable. So it's a classic trade-off, right? Guaranteed stability versus raw speed.
Okay, so we've gone through the how and the what. Let's zoom out for a second and talk about the so what. Why does any of this really matter in the big picture?
If there is one core idea to take away from all this, it's this right here. The power of a digital filter isn't in the silicon chip itself, it's in the software. A single processor can become a dozen totally different filters just by loading a different program into its memory. That is the revolution. So at the end of the day, it's this. From a simple recipe of just 3 basic operations, add, multiply, and delay, we get the incredible power to fundamentally reshape our digital sights and sounds. It's a stunning example of how simple, elegant building blocks can lead to unbelievably complex and powerful results.
So you see these filters, they don't just clean up signals. They are editors of our digital reality. They choose what to amplify and what to ignore. And that leaves us with a huge question for the future. As our power to filter information becomes almost limitless, what will we choose to let through?